All right, welcome back. In this set of videos, I want to look at the real business cycle model again, and I want to do a small extension by adding investment friction. And remember that we had a problem with RBC. Well, there were many problems with RBC, but two of them were related to investment. So first was that investment was very volatile. Remember when we looked at the variance-covariance matrix of the different variables following technology shocks, investment moved the most out of any variable. So investment was very, very volatile. And the second problem was that the IRF for investment did not match the empirical evidence. How so? The IRF for investment looked like the standard AR1 decay plot. So after we hit the economy with a technology shock and we look at the trajectory of investment, it jumped up in period one and then exponentially decayed. So it looked something like just your normal AR1 process. Every period we get, then we have rho was less than 1 and greater than 0, right? Otherwise we would have like a sawtooth thing. But every period we get smaller and smaller, and we smoothly reconverge to the steady state, which in the log linear approximate case is 0. So it's 0 here only because we're doing the log linear approximation. But recall that in the data, we saw a plot that looked more like something with intertemporal smoothing. And what does intertemporal smoothing looks like? It looks like when you get a shock, it jumps up partially, and then it climbs to its ultimate maximum, and then it slowly decreases. And this is, I'll call this the intertemporal smoothing case. Intertemporal smoothing. Why? Because each value is something like a weighted average between today and yesterday. And we saw a plot like this in the RBC model for consumption. And that comes from the Euler equation, which weights present and future consumption based on the rental rate of capital. So we would like to bring this kind of intertemporal smoothing into investment, and in a way that's going to reduce volatility. And we saw in TD, and you also saw in class how to do this. We're going to do this with a smoothing function, with a penalty function, I should say. And the penalty function will introduce smoothing because it's going to be a function of investment today and investment tomorrow. So remember, we're going to build this phi function, and phi is going to be a function of it and it minus 1. And we would like phi to have these properties. We want that phi is equal to 1 when it is equal to it minus 1. We would also like the maximum value of phi should be 1. And we would like phi to be symmetric. So we don't care if it goes up or goes down. Phi should change by the same amount if it changes relative to it minus 1. And we already saw in class what was phi. Symmetric, of course, should right away make you think about quadratic, and indeed phi is quadratic. We're going to define that phi of it and it minus 1 is equal to 1 minus gamma over 2, 1 minus it divided by it minus 1 squared. So you can see we have a negative quadratic here. So this is going to be a downward facing parabola. The maximum is 1 because parabolas will take their maximum at 0 and we're going to shift it. So it's going to have a maximum value of 1. And it'll cross 0 somewhere. So in essence, this there's going to be a bunch of negative values here, but of course the agent will never choose these because of how we're going to use phi. We're going to inject phi into the law of motion of capital. So we're going to take our law of motion of capital, which normally looks like this. And this equation says that whatever investment we choose here, it's all going into kt plus 1. If we choose 10, we get 10. If we choose 20, we get 20. And we're going to change this. We're going to change this to become something like this. Kt plus 1 is going to be 1 minus delta kt plus phi times it. So you see, if an agent chooses something where phi is negative, then of course they will lose capital. They won't gain capital at all. So the agent will never choose anything down here. So in essence, we can think about this as like a cutoff parabola. And indeed, we can look at the function quickly. I prepared. Okay, so like a super genius, I didn't put audio in this part. So I'm voicing it over later, and hopefully that's not too distracting. So what are we looking at? We're looking at a graph of the penalty function, which is shown in orange, and also the t plus 1 capital that results from the choice of investment, I, in green. So in the beginning, g, which is gamma, is set to 0. So the penalty function is just always 1. There's no penalty. And you can see that the green line is just a straight line, a linear function of x equals y. So no matter what we choose for investment, that much investment goes into next period capital. You choose one investment, you get one more capital. Now, if we increase g, we see that that's no longer the case. So focusing first on the red parabola, that is the degree of penalty. Let me figure out how to work Desmos here. If we choose 1, which is that capital today is equal to capital yesterday, because just in this example, it shows capital yesterday was equal 1, that's the k variable, then there's no penalty. You get everything that you put in. However, if we deviate from that choice of last period, either in the positive or the negative direction, then we receive a lower amount of capital than we actually chose for investment. We paid to get 1.5 units of the investment good, but only 0.87 of those units will end up into our next period capital stock. So this is what's meant by friction. Okay, and now in green you can see what will the actual quantity of the next period capital stock be. Remember that in the base case it's a straight line, so pretty much everything between 1 and like 1.5, it looks like it's almost a straight line there. Kind of where I have the arrow, it starts to bend off and go down. So the best choice for the agent is to stop at 1.5, something like this. Even if he wants to invest more in the next period, he shouldn't. He should spread it out over time. This is the effect of the friction. If the agent chooses something that's higher than that 1.5, then there's this diminishing returns. You can see that if you try to more than double your investment, so the agent tries to invest 2.75, then actually nothing will end up in her next period capital stock. So it's not intelligent to choose something that high. And we saw also that this can be negative, this penalty function, but that doesn't make any sense. Why would you buy 3 units of investment good just to have your capital stock actually end up being subtracted from? So from the perspective of an optimization problem, it doesn't matter that this red parabola goes under 0 because you'll never choose that. And yeah, that's pretty much what I wanted to show with this small demonstration. I guess, here I'm showing you that when g increases, the rate at which you get to that cutoff line also increases. So the penalty function gets skinnier and steeper. So before we could invest up to like 2.5 times what it was last period. So last period was 1, we go up to 2.5, then we get 0, that's the cutoff. Now the cutoff is only like 1.5. And indeed, the straight line coming out of 0 no longer is straight at the same place. The linear function is kind of shifted to the right as a result of increasing g. So you can see that as g increases, then the agent's choice of investment is going to become smaller and smaller. They're going to push their investment choice. They want to spread that investment over a longer and longer time because they can only invest a little bit each time period without incurring that
So-
big penalty. In the next video, we'll see how to plug it in. And I guess between now and then, I encourage you to walk through this problem again. Of course, we've already seen it. You've seen it in the notes. Take this law of motion of capital function that I've defined here, this one, and solve the household problem. And that's what we'll do in the next video. I'll see you there.